Do the thing.
Good. Okay, so we are nearing the beginning of integration, so I just want to wrap up some L'Hopital's rule stuff. I have a few warm-up problems, just kind of garden variety, differentiation, and optimization things. Then I just want to sort of illustrate the different contexts in which L'Hopital's rule applies. So we've already proven this one, where if f and g go to 0, then their quotient has a limit whose value is equal to the quotient of the derivatives at that point. But there's some other variants of L'Hopital's rule that involve limits at infinity, which is good because we defined those carefully last time. So we'll do some of those, and then I'll prove L'Hopital for this very nice case, infinity over infinity, which is good because infinity over infinity at infinity, as I call it, but which I'll explain more carefully, is what you need to prove things that we discussed last time, like end behavior. That, I don't know, if x goes to infinity, then this thing goes to 3/2. So it's good to prove that, but proof's a bit of a bitch. Okay, so first some warm-up problems, which I will mostly ask you to do. But okay, so here's a nice problem statement. I'll do a little drawing for you and then ask you what I should do. So we have two cars who begin at an intersection, which for convenience I'll put at the origin, at time t equals 0. And they both start with velocity 0. So you can think of this as two cars at the intersection that are, at a dead stop, right? At time t equals 0, they both hit the brake. There's that brake. They both hit the gas, so they begin to accelerate. So one is accelerating due north at 8 meters per second squared. The other is accelerating due east at 5 meters per second squared. And we're interested in the question, after 6 seconds, what is the rate of change of the distance between the two cars? So not their position north or east of the origin, but we want this kind of hypotenuse, which I call d of t, the distance between the two cars. So, okay, first thoughts. What do you think we should begin with to tackle this thing?
I'll start with the question. Is this after or at?
Uh, those two things mean the same thing.
Okay.
After 6 seconds means t equals 0 plus 6 seconds, or at 6 seconds means t equals 6 seconds, but 0 plus 6 equals 0, so they're the same.
Okay. Just clarifying because reasons.
No, it's good. It's important.
I believe that the right now we're thinking in terms of acceleration. So we are going to have a change of acceleration where we see I think I believe our end unit is going to be acceleration.
Let's see. By
I'm
end unit, you mean
confused.
the answer?
Yes.
Well, let's see. This distance has unit of meters, and what we're asked for is the rate at which the distance is increasing. So I think what we're looking for is d dot, which has units of meters per second. Not
Okay.
meters per second squared. Yeah.
So not position, but not acceleration. The thing in the middle. Oh, yeah.
Velocity.
Okay. So I guess we can start by finding d double dot of t to be equal to what the Pythagorean theorem applied to this. So I guess I'll start listing off math now. So d double dot of t is equal to the square root of
Damn it. Sorry.
I. How do we think of 8 meters per second squared being squared?
I guess you would square the unit as well if you were doing that. So you'd say 8 meters per second squared, all quantity squared, and then 5 meters per second squared, quantity squared. So let's see, is that what you're
Yes.
asking or suggesting?
I'm just curious how we would we have meters squared over seconds to the power of 4?
Yes, yeah, those would be the units. Meters squared over seconds to the fourth.
That is weird. Well, I guess the square root on
Yeah, the square root will kill one of
do
those
that.
factors, right? So let's see, what's this numerically? 64 plus 25 is what, 89? So this would be what, 89 meters.
Squared over seconds to the power of 4.
Good, yeah. Now the square root of meter squared over seconds fourth is meters per second squared, right? So I'm just going to pull the units outside but leave the number inside. So this will be meters per second squared.
Okay. And
Okay, so I want to pause though and ask whether we think this is true, because this is using the Pythagorean theorem, which is a statement about distances, right? So this is an acceleration, which is not a distance. So is this. So I want to do a sanity check just to convince ourselves. Is it actually true that d double dot is going to be root 89 meters per second squared? Because it's not totally clear to me that we can apply square roots to accelerations like this. So we know that it would be true. Maybe this is actually right, but let me just think. So we know that d, the distance itself, would have, let's see, d squared equals, I don't know, we can use x for this car and y for the other car, right? So x squared plus y squared. So if I take one dot, I would have 2d dot equals 2x x dot plus 2y y dot. Then if I took another dot, after killing the 2's, kill all the 2's, then I would have, let's see, product rule on the left, so it would be d dot squared plus d double dot equals, same thing here, I guess, x dot squared plus x double dot plus y dot squared plus y double dot. Okay. So we're trying to argue that d double dot is supposed to be this thing. Now, I'm not sure that's actually going to be true. If we solved for d double dot here, I'm not sure we would get the square root of, what's this, x double dot plus y double dot? So is it true that d double dot equals square root of x double dot plus y double dot? I actually don't think this is going to be true, right? Because we have these extra terms in here. Maybe I'm wrong. Let's see, does this actually work? Well, let's just see if we get the right answer and then we can come back to it. So if this were our d double dot, then you would integrate and say d dot is supposed to be this thing times t, right? Root 89 meters per second squared times t. And then I would plug in t equals 6 and get 6. Maybe that's actually true. I think, yeah, the right answer is 6 root 89 meters per second. Why the hell does that work? I've confused myself. Do you have any thoughts or insights on this, since this was your proposal?
Why wouldn't the Pythagorean theorem work here?
Apparently it does, so maybe I'm just confused. But the reason why Pythagoras might not work for these derivatives is because you would get these cross terms. So I've tried to convince you in the bottom that we shouldn't a priori expect that Pythagoras should work, because you know Pythagoras applies to lengths, right? The sides of a triangle. So if you wanted to double check whether Pythagoras applies to accelerations, which are not lengths, right? This is something different. If you wanted to check whether that was true, then you would try to prove it by saying, I know Pythagoras is true for lengths, and then I would take two derivatives of all of the lengths to see whether Pythagoras is also true for accelerations. And naively, the calculation I've done here, now I've confused myself because I don't think it actually does work, but apparently it gives us the right answer. Is this because I'm very confused about this. Let me see. There's something special about this problem, which is making Pythagoras work for accelerations here, right? Because Well, okay, so let me, I guess we've solved the problem, so that's all I have to say about this. But let me give you one example to try to convince you that we shouldn't necessarily expect Pythagoras to work for accelerations, right? So let's say I have some particle that is at, it moves around in the plane, so at each time it has an x coordinate and a y coordinate, and I'm just going to make up some random things for these guys. So maybe x of t is going to be like, I don't know, cosine of t, and y of t will be t squared plus 1, right? So we would then be able to differentiate and say, well, we know x double dot y double dot would be, well, two derivatives on cosine, which could be a minus sign and then a minus cosine, so minus cosine t, and then this guy would be, let's see, 2t and then down to 2. So the Pythagorean theorem applied to this guy's distance from the origin would tell us d at time t is square root of, well, the square of the first one plus the square of the second one, t squared plus 1, quantity squared. This is true, but Pythagoras applied for the accelerations would say, is it true that d double dot is, let's see, square root of cosine squared, because the minus signs cancel, plus 4. So only one of these can give the right answer. If I take two derivatives of this guy, the question is, if I take two derivatives of this guy, is it going to match this thing? And I don't know how to do it without just writing out a whole bunch of derivatives, but it seems to me that it's not going to match. Well, let's just do one step and see if we can get it to match. I guess, what would this be? D dot is 1 over 2 root of all that junk, and I'm not going to write it out again, times 2 cosine t minus 2 cosine t sine t. Yeah, I'm getting to the point where I don't want to differentiate this again because it's becoming a mess. But the point I'm trying to make is, imagine taking this mess that I wrote down and differentiating it again to get the acceleration. And you're telling me that if Pythagoras works for accelerations, after I differentiate and take that huge thing, that I'm going to get this very short expression? That seems unlikely to me, right? I don't know, maybe I'm wrong. Apparently, at least in this case, I'm wrong. So do you have a counter argument for why you think Pythagoras should work for accelerations?
I have no valid argument.
Okay. Yeah, this is a little mysterious. Oh. Is this why? X. Yeah, oh. I think I have an idea. I think, yeah, this is a special case because the motion of the two guys is perpendicular, right? One guy is always going north, the other guy's always going east. So when you write out this ugly shit, I think we're going to have a cancellation. Because I think some of these x dot squareds and y dot squareds pieces are going to go away. So, okay, I have to think about this more for next time, actually. Maybe I'll have an errata thing on the next meeting, because it was an interesting idea, and I'm confused now as to why this worked. But, okay, apparently it was good thinking, so I got the right answer. So, well, let's see an alternate way to do it. So, if we said, I don't know why Pythagoras should work for accelerations. I know Pythagoras is a statement about physical lengths of triangles with lengths of meters. If we were being very conservative and said that, then what you would have done is started by saying, well, the first guy is accelerating with, 8 meters per second squared. So you would integrate, you would say, okay, he's at y double dot is 8. I'm not going to write the units, but that means y dot is 8t, and y of t is half of this would be a 4t squared. So you would integrate up to get his position. You would say the x double dot guy is, 5. So x dot is 5t. So x is 5 halves t squared. So you integrate up and get his position, and then you would say Pythagoras applied to the distances between them gives me this thing. And then when I do some simplifications, there's a t to the 4th inside, which gets pulled out to t squared. There's a 16 plus 25 over 4. Oh! No, that's not why. Damn it, I thought I understood why this worked. Okay, well anyway, so this would be the d, the distance as a function of time. You would take the derivative, pull down a 2, and get the answer, which we wanted, which is this root 89 thing. So that's actually very interesting. Okay, I have to think about why this is true. Why can we just use Pythagoras for accelerations? All right, well, I have nothing else intelligible to say about this. All right, thoughts on this question? Did you mute yourself?
I did not mute myself.
You just had nothing to say, or you felt dead inside?
Going fine for now.
Okay.
I have no thoughts.
Okay, well, since I'm confused on that one, let's do a different one. So, suppose there's some rope that you are climbing. So you can think of this as like a game. At each time you get to make a move, and the move is deciding how many feet you want to pull yourself up. So say at this, at the first round, so round 1, you choose to pull yourself up by 2 feet. So then you go, let's see, since you're climbing, you choose to go up by 2 feet, then you move upwards by 2 feet, but the rope is not securely fastened. So since you chose to go up by 2 feet, the rope is going to slide down by the cube of that number of feet. So you go down, I don't know why I wrote my F that way, but you go down by 8 feet. So at each time you pick how much you want to go up by, and then you slide down by the cube of that. So if that's true, what number x should you pick? So what should your strategy, your move be, to go up the rope to climb as quickly as possible? What should we do?
So worded differently, we want to find the value x. I don't know. Never mind. Couldn't remember how I was going to word it.
Deep thinking.
Well, we certainly want to lower ourselves, and it would seem that pulling up by more than 1 foot is counterproductive.
Right, okay. Good first observation. So we know whatever the answer is, x max, or whatever. Maybe not max, I should call this best, right? The best move or something. But whatever the answer is, it has to be less than 1, I agree. And I don't think it should be 0 either, because then you never get to the top. So we have a range. That's good. Now what? So what should we do to find which x in this interval from 0 to 1 is the most efficient?
I guess we can start by writing a formula representing our position after a movement.
Okay, good. What's that function?
You choose the worst time to come down here. Regardless.
Is it a human or a dog?
Human.
Oh, okay.
So I guess we can simply say p of x, where p equals position. You know what I'm trying to say. P of x equals x minus x cubed.
Okay, looks good.
Current position. Well, p sub c, I don't know. It's just a constant, basically.
Okay, yeah, that looks right to me. So if you make a move x, this is how much height you gain, basically. So then what should we do to find the most efficient move choice?
Find some points where this is maximized.
Good, okay. So how should we maximize?
We can get by taking the derivative and seeing where that equals 0.
So PC prime. Good, what's that?
Yes. This is simply going to be 1 minus 3x to the second.
Okay, and you say we want that to be 0? Okay, so what do we get for critical points then?
So we are going to have, by algebra, I guess, solving for this equaling 0, 3x squared equals 1, and I guess square root of 1/3, so 1 over root 3.
Good, yeah. So in particular, we take the positive root, because climbing downwards is probably not a very good strategy. Okay, so how do we know this is the winner? There's two ways to make the argument. One, you could say, well, this has to be the maximum, because there's no endpoints, right? We're on the interval x is in 0, 1, so there's only three choices. It's either an endpoint, a place where the derivative is undefined, or a critical point. So one thing you could say is, I know this is the max, because there's no endpoints, and no places where the derivative is undefined, and this is the only critical point. So you could make that argument.
We can also back it up by checking that it's concave.
Ah, good. How do we do that?
There's going to be second derivative is going to be equal to negative 6x, and by inserting 1 over root 3, it's negative.
Good.
Which means that's concave. Woo.
Yeah, so if it's concave, then certainly this has to be a max, right? Because it opens downward. Very nice. Okay, that was fast. Good. So as you say, write down a function, maximize this. I guess I technically put infinity here, but you should maybe I should have thought of your argument that 1 is probably above 1 is a bad choice, so you can actually truncate this, use a smaller interval. But whatever.
Also, if you can pull infinity of rope, you're doing pretty good.
Yeah, that's true. You're pretty swole if you can pull infinity feet. Oh my god. Okay. Good. So, yes, as you say, this is the critical point, and precisely as you suggested, the second derivative is negative here, so it's concave, or concave down if you prefer. So you should do that. Good. More thoughts on this?
I have no thoughts.
Nice. Alright, one more. Okay, so we look at, through our telescope, at this planet, which is assumed to be a perfect sphere. And we're going to look at it, with our human eye here, human eye through a telescope. And we're going to measure using the telescope what we think the diameter. So we get some measurement of the diameter of this distant planet is, which we say, okay, that it's about 2,000 kilometers. But we know that the telescope isn't perfect. It introduces some measurement error. So it's plus or minus 1%. It could be 1% bigger, 1% smaller. So I'm going to signal a strategy here by using the word estimated. But what is the estimated percent error in the computed volume of the planet, not the diameter? So if you know the error in the diameter, what's the estimated error in the volume? Good. So what should we do?
So we know by our very exact measurement error that our diameter is in the range of 1980 to 2020.
1980 kilometers to 2020 looks good.
And I am inclined to believe that we can just solve for volume for each of these points and compare it to a known 2000.
Ah, okay, so you say I write down a function for v as a function of d. So what's that formula? What's the volume?
It is going to be thinking. Don't know why I had to think so hard. It would be 4 over 3 pi radius cubed.
What's the radius in terms of the diameter, though?
Is going to be d over 2.
Looks good. So then this is what, d cubed, got an 8 downstairs, so 4 over 8 is a half, half times a third is a sixth, so I think this should be pi over 6 d cubed, is that right? Okay, and then as you say, what we could do is then take these two endpoints, the highest it could be and the lowest it could be, so you would say the percent error in the volume.
I apologize for...
Do you have to do a thing?
D over 2 out of the parentheses.
Wait, sorry, say that again?
The d over 2, even though it is in parentheses to a power, is what occurred there? I need clarification.
Oh, this is d over 2 cubed, so that's d cubed over 2 cubed, which is d cubed over 8, and then there's a 4/3 outside, so 4/3 times 8. Oh, sorry, 8 down. why am I saying times 8? Times 1/8. 4/3 times 1/8 simplifies to 1/6, right?
Okay. That makes more sense.
Good. Math. Okay, so then as I think you suggested, you would find the kind of two endpoints, the highest and the lowest this could possibly be. And then since we want a percent error, to get a percentage, you divide by the volume itself. So you would have this delta V over, what would it be, I guess? Whatever V of 2000 is, I guess. So V of 2000 I don't want to plug in. But I guess that would be, since this is the pi over 6, so you say we would do pi over 6 times the big one, 20. The kilometer, we can kind of see that we're going to have kilometers cubed upstairs and kilometers cubed downstairs, so the units will cancel, so I'm just not going to write them. So we'll have this thing minus, what's this, pi over 6 times 1980 cubed over, what's this, pi over 6 times 2000 cubed. Okay, so now suppose you don't have a calculator. You want to get an estimate of what is this number. What do you think we can do?
L'Hopital's rule only applies to limits, is that correct?
Yes, sadly.
I believe we can factor out pi over 6 from all of this.
Good.
I don't know why I said factor out. Basically cancel out.
Yeah, that's fine.
And I guess take the cube root of this entire thing?
Well, we don't want to take the cube root because the thing that we've written on the right side here is what we're trying to solve for, right? This is the answer we want. So if we take the cube root, then the left side will have the cube root of the answer instead of the answer, right?
I'm thinking potentially undoing the cube root later.
You're thinking of doing the cube root later.
Or,
what do you mean?
Actually, no. Factoring out the cube, no. That doesn't work. Because we have this minus 1980 cubed. Never mind.
Are you saying by factoring, are you saying I want to split this into two guys and put like a 2020 over 2000, and by factoring out cube, is this what you mean? You put all of the 2000 guys in the denominators of these two? Is that what you meant?
That is not what I was thinking at all, but it does work.
Okay, yeah, this gives us something. So,
and don't lose the... Oh, wait. Never mind. We don't need to worry about the pi over 6 because it was both top and bottom. Okay, never mind.
Yeah, those are all gone. So, if we're just trying to estimate, so one way to do this is to say, well, this is 2000 plus 20 over 2000, right? So this is basically 1 plus 0.01, right? Because that's the 1% error. So this thing cubed minus, what's this, 1 minus 0.01 cubed? Is that right? So, okay, so I claim we have a trick. We learned a trick for doing something like this where h is small, and I think 0.01 is small enough that we can use that trick. So,
right.
What do you think we should do?
Attempting to remember. The tangent line approximation, as I can't choose whether to be close or far away from the mic. Trying to remember the tangent line approximation, because that might be useful. Oh, what's in the top of the screen?
Maybe I'll just kind of secretly drop this little John up here, so I think it looks like that. Is that right? Yeah.
Yeah, that looks totally... Yeah.
So
Is that... Was it a minus h? All, like, in the end? Well, h minus a.
was it
Rather than h.
Oh, are you saying in this formula, is it supposed to be a minus h?
Well, on the right side.
Oh yeah, down here. So down here you'll plug in h equals negative 0.01, but the tangent line approximation works as long as the absolute value of h is small, right?
Oh, okay.
So that's fine.
I was thinking, like, specifically this f prime a times h part.
Ah, yeah, so I agree. We'll have to use different h's in these two terms if that's what you're getting at. It'll be negative for one of them.
No, not that either. Okay, maybe I'm just not remembering it right.
Oh, are you asking whether this formula is correct?
Yeah.
I'm pretty confident this is right, yeah.
Okay, probably use it on a daily basis.
Something like that.
Something.
Okay.
Trying to remember. So we're going to have that for f of x equaling x cubed, we're going to have about 1 plus 3x. Excuse me. Lots of loud noises at once.
Woof, woof, woof!
Yes, lots. Okay, back to trying to understand things. This is going to be 1 plus 3, begin parenthesis, 1 squared. So just 1 plus 3 times 1, basically. Times, trying to remember, 0.01.
Good. 0.01. Then we have a second piece, I think.
Now I'm going to mute myself.
How will we know what the second piece is if you're muted, though?
Got nothing done. Okay, and similarly, 1 plus 3 times 1 squared times negative 0.01.
Good. Running out of space, but that looks right. So now some magic happens. The 1 cancels, and the 1's there. And then we're left with, well, 1 squared is 1, so I can just drop those guys. So what do we get at the end of the day?
It seems that this is going to be... It looks like it's going to be, if I could choose my words carefully. I think it is going to be 0.06%, if that is...
Well, just 600ths, so this means 6%, right?
Ah.
The percent means hundredths.
Oh, yeah.
Good, so, yeah.
Wow, that's a big error.
Well, we should be careful because 6% was the highest minus the lowest. So the true plus or minus would mean this is plus or minus 3%, right? Because if the whole range from the biggest possible to the smallest possible, if this whole range is 6%, then of course when you say plus or minus, then you only say, well, that's from the middle to one end. So 3% is the what you would call the statistical error here. Good. Okay, so that was very nice. I liked your strategy of starting with the highest and the smallest and subtracting. It's different from what I did. In practice, say, when I was computing errors when I worked at CERN, like errors for some of our analyses, often the functions are way too complicated to differentiate. So you use exactly this strategy, where you say, I have no idea how to do tangent line approximation, so I'm just going to take top minus bottom and cut it in half and say that's the error. So that was very nice heuristic thinking. So we got the right answer in the end. I'll show you another way that one could do this, which starts with the tangent line approximation at the beginning. So you could have said, we know volume is a function of diameter is this guy. I'm going to use the tangent line approximation, right at the beginning, applied to the function v of d plus delta d, where this is the error, say like the 1% error in d that we get. And you say, well, that's going to be v of d plus v prime of d times delta d. So the measurement error, which is this v of d plus delta d minus this v of d, why did I put epsilon there? Changed my mind about what the small number is. This thing is roughly v prime times delta d. So the only reason I'm showing it to you this way, even though the previous solution that we just did works, is that this gives us a very nice formula for measurement errors that works for any function at all, right? Nowhere in this derivation so far, well, we stated it, but I haven't plugged in what the function v is yet. So this thing works for anything. Any function f, so if you're measuring any quantity, any function f which is measured will have this so-called error propagation relationship, which tells you that roughly the percent error in the function, which is some function of whatever you measure, the percent error, which means the error in the function divided by the function, is always going to be approximately the derivative of the function times the error in whatever the dependent variable is, the x, over still over f, yeah. Don't forget it's all over f, because we divided both sides by v in this guy. So this is very nice, because even if it's not a volume, you can just remember this, that whenever you calculate some quantity from a measured quantity that has errors, this is how the error propagates. So error propagation propagates the error from x to f. Propagation. Okay, but then, of course, this has to give the same thing that we found a moment ago. So when you plug in the specifics for this problem, v prime is, of course, this pi over 2d squared. This pi over 6d cubed downstairs. Those cancel. We get a 3 delta d over d. Delta d over d is 1%. So all we have to do is plug in 3 times delta d over d is 1% to give us a 3%. So the other nice thing about this solution is notice that nowhere in this problem at all did we have to use the number 2,000 kilometers. Right? In the previous one we plugged in 2020 and 1980, so we explicitly used the diameter. The nice thing about this solution is it reveals to you that at the end of the day, that number 2,000 did not affect the answer to this problem. The answer at the end of the day was just 3 times the percent error in the diameter. It doesn't matter what the diameter itself is. It only depends on the percent error in the diameter. So that's kind of cute. You get to see which parts of the problem statement actually mattered and which were extraneous detail. This is kind of fun. Okay, thoughts on this, John?
I have no thoughts.
Okie dokie. Alright, let's do some more L'Hopital stuff. Okay, so what did we prove the first time? The first one in our orgy of variations here was what I call the 0 over 0 at a version of L'Hopital's rule. So we proved this, I think, a couple times ago, that if f goes to 0 at some point a, some finite point a, and g goes to 0 at that point, and the limit of the quotient of their derivatives at a exists, it has to be on some interval surrounding a but not necessarily including a, as we saw, then we get this nice L'Hopital relation where the limit of the quotient is the limit of the quotient of the derivatives. And of course, remember there was the hacky proof that I said you can think of this as f of a plus f prime of a times x minus a. If you want to use a tangent line approximation to sort of explore why L'Hopital's rule might make sense, you would put these in the top and bottom, and then you would say, well, we're assuming that f goes to 0, g goes to 0, and then these things cancel. So you get f prime over g prime. I should put quotes around this because it's a little sketchy. Anyway, so we already proved that. That's the vanilla version of L'Hopital's rule. Now there we'll see some kinkier versions of L'Hopital's rule besides the 0 over 0 at a1. So one variant is not a limit as x approaches a, but a limit as x approaches infinity, which we defined pretty carefully last time. So if, as x goes to infinity, f of x goes to 0, and the same is true for g goes to 0 at infinity, and the limit at infinity of the quotient of their derivatives exist, then we have another L'Hopital relation, that the limit at infinity of the quotient is the limit at infinity of the quotient of the derivatives. So because this variant assumes they both go to 0, so 0 over 0, and the limit is at infinity, I call this 0 over 0 at infinity. Right? Not rocket science. But one other harder version to prove is that if f goes to infinity and g goes to infinity at infinity, so both of these guys get huge, right? F and g both blow up at infinity. But the limit as x goes to infinity of their quotient, the quotient of their derivatives, I mean, exists, then you get another L'Hopital. The limit as x goes to infinity of the quotient is the limit as x goes to infinity of the quotient of the derivatives. So since they both go to infinity, top and bottom, I call this infinity over infinity at infinity. So, okay, there's actually more. I call it an orgy of variations, but this isn't much of an orgy with just 3 people, or 3 theorems. There's actually a bunch more that I think are less interesting, so I'll just kind of cite them towards the end and prove these, because I think, well, we already proved the first one, but I think these second 2 down here are kind of the more interesting of the variants, right? Okay, thoughts or comments on the orgy?
Yes, lovely choice of words.
I actually took this word from Spivak. He uses in his book, he says, this completes the orgy of variations of L'Hopital's rule.
In a totally serious textbook.
Oh, certainly, yeah.
Okay.
I mean, you now know that physicists talk about kinks, and Gautam and I discuss slowly wiggling the nut, so I think an orgy should be seen as relatively tame by comparison.
This is all occurring while Mason is weightlifting.
Well, he probably can't hear me talking about orgies, though.
He's 3 feet away.
Oh, maybe he can then. Good. Other comments?
I have no comments.
Okay, then let's... I think I baked in a challenge, so before we even prove these, let's assume that we have them and use them to show something. So we spoke last time about domination, that f dominates g if the limit as x goes to infinity of their quotient, x goes to infinity of g over f equals 0. So f grows faster than g. So let's prove that any non-constant any non-constant polynomial. So that means it could be linear, it could be x squared, it could be 3x squared plus 5, any polynomial that is not just a constant term. So you might believe that any such polynomial is going to dominate square root of x, right? Square root somehow, when you take the square root of a number bigger than 1, the square root makes the number smaller, right? So this thing is somehow, we would think of as, decreasing, not decreasing, he's increasing less quickly than polynomials, right? You might naively think, okay, x squared makes stuff bigger, square root of x makes stuff smaller, so as x gets very large, we would think that, square root of x over x squared goes to 0, which indeed it does, because in this case it's quite obvious, this is just 1 over x to the 3 halves. And as x goes to infinity, the bottom gets huge, and that goes to 0. But we want to prove this rigorously for any polynomial, maybe call it, I don't know, p of x. Fuck, no, I used inconsistent notation here. Yeah, sorry, this should be maybe in the denominator p of x, and I shouldn't call this f, I should just say, this is the function square root of x. Okay, anyway, so suppose we want to prove this, what should we do?
I guess we can begin by calculating it. Oh, It says we can use any L'Hopital.
Yes. So which one in the orgy do you think would be productive to use?
I believe number 2.
I think so, yeah, because square root should be going to infinity, polynomials go to infinity as we proved last time, and we can see whether the quotient of their derivatives works. So, alright, let's try that.
We begin by taking the derivatives of the top and bottom by L'Hopital. Root of x derived, well, I don't know why I almost said derived. The derivative of root of x is going to be equal to 1 over root x. Well,
1 over 2 root x, right?
Yeah, correct. Makes more sense. I'll take care of the fractioning stuff, or you will, I don't know, later. And the bottom p of x, we just get p prime of x.
Good. Okay, and what is the fractioning stuff you would like to take care of?
It's going to be equal to 1 over p prime x times 2 root x.
Good. Okay. Ooh, why did I put that fraction bar as a square root? Okay, so we want this to go to 0. So Can you explain why we should expect this limit to go to 0?
We want it. It would seem that we have this in the reverse order. Well, for what I'm used to. Let's see.
The reverse order. You mean the chain of equalities here is reverse?
Okay, we wanted to be equal to 0 to show that the, how do I word it? That p of x dominates root of x, as we see on the left side. I was trying desperately to remember the definition of dominates.
Ah, right, yeah. Yeah, so if we can prove this is 0, then that's what we wanted to show. That's the conclusion. Right, so, good.
But this seems like it almost... Oh, wait. P prime of x, unless it was... Nope. Even then, I was thinking about if p of x was linear, but in that case, the 2 root x would still approach infinity.
Yeah, good. So you're saying that at worst case, p was linear, so this guy is a constant. P prime is a constant. So then you could pull the constant out of the limit. This would be 1 over 2c times the limit as x goes to infinity of 1 over root x. And that has to go to 0. I mean, the proof would be very short. You would just say, we're trying to prove that this goes to 0, so like, I don't know, let epsilon greater than 0 be given, and then choose n, so 1 over 2 root x less than epsilon, or I guess this would be, you'd move x over x, I'm just exploring here, but you would want n to be greater than 1 over 2 epsilon squared, right? So then that would prove that this thing goes to 0. So I don't really want to write that out carefully, because I think it's pretty obvious that square root of x goes to infinity at infinity, so 1 over square root of x goes to 0 at infinity. Right? So that's the worst case. If p was not linear, then you get even more stuff that gets large in the denominator, right? You get x's and x squareds and so forth. And we proved last time that those guys, polynomials, go to infinity at infinity, so 1 over the polynomial should go to 0.
So, do we need to go into any more detail, or is that statement all we need to refer to?
Yeah, I think that's enough. I was being a bit sketchy in making that argument about why it goes to 0, but yeah, if you buy that, then we're done. And then if we showed this goes to 0, then we proved that any non-constant polynomial dominates square root. So that's all. Good. Let's see that one more time. So, as you said, we're using infinity over infinity at infinity, the last L'Hopital rule. So, by that result, which we haven't proven yet, this limit of a quotient is the limit of quotients of the derivatives. X to the 1/2 it gets differentiated to 1 over 2 root x. There's an f prime or p prime downstairs or whatever. And then one can argue that this is 0. I was lazy here and just said the proof is easy. But, I mean, you could write it out if you wanted. Okay, thoughts on this guy?
Oh wait, I muted myself that time. Good job. I do not have a
Okay.
spelled without a U.
Wait, what'd you say?
What?
What was that last thing?
Spelled without a U.
Spelled without a U. Did I spell something wrong?
I was commenting on my own spelling of thoughts.
Oh, okay. I thought there was something wrong on the slide. Okay. Good. Thought T-H-O-T. Like that hottie over there. Okay, so here's a more interesting challenge, I think, that uses L'Hopital rule in a somewhat surprising way. So this will also plug in one of the gaps in our reasoning before. So remember way back in the day I was wringing my hands and being a little nervous about our proof of derivative of e to the x being e to the x, because to do that proof, I used this sketchy definition, right? I said we're going to call this e. E is this limit as x goes to infinity of this 1 plus 1 over x, and I made no attempt to argue that this was the same as the base of the natural log or any of the other definitions that we did before. So this exercise won't totally fix that. I think we'll do that after integrating, when we do integration. But this will connect at least one of the gaps, the showing that this limit exists and it's equal to the base of the natural log. So that's something good to show. So we'll do it in steps. I've scaffolded it for you. I'll ask you to walk me through what to do at each step of the scaffold. So the scaffold suggests that to do this proof, we should start by defining a new variable y, which is the thing inside the limit of my sketchy definition. So y is 1 plus 1 over x to the x. And then the scaffold suggests write log of y as a quotient of two functions of x. So it's one thing divided by another thing. So what should I do?
Oh, so I guess we are taking the log of y, which means that we're going to have log of that chunk is equal to e to the power of 1 plus 1x equal, e to the power of 1 plus 1 over x equals x.
Well, hold on. We're taking the log of y and not of e, right? So I think we just want to take the log of both sides of this equation.
Oh, yeah.
Good. Okay, how do we simplify the left then to get a quotient?
Power. I believe that we can start with the trying to remember. I guess just power rule to see that x log of junk equals log y.
X log junk, okay. Sounds good. And the scaffold is asking us to write log y, which is this junk on the left, as a quotient of functions of x. So right now it's a product of functions of x. Do you see a way to rewrite this so that it's a quotient with a top and bottom?
I think we could multiply by x to the power of -2, and that kind of satisfies it.
X to the -2. Okay, so then there'll be, well, you mean multiply by 1 with an x to the power -2 top and bottom? Because we can't just multiply both sides of the equation by whatever we want, right? We're trying to write log y in something. So I don't think we can just multiply it by x to the -2, but we can multiply by 1 in a clever way that doesn't change the right side.
Right. So that is going to result in x to the -1st log junk over x to the -2.
Yeah.
My voice died there because
I thought that was intentional because of the oddly high-pitched voice comment that we say when making, confused statements.
It was on high pitch, and I just stopped talking.
Good. Okay, so this works. We could actually use this, and the result would be the same as what we would do the way that I solved it before. Just for ease of calculation, I would like to suggest that instead of multiplying top and bottom by x to the -2, we just multiply top and bottom by x to the -1. Just because there's less stuff. What'd you say?
Yeah, it makes a lot more sense.
No, it's fine. Your way works too.
Thinking about just undoing the x and bringing it to the bottom somehow, but that also prevents us from just multiplying by 1.
Yeah, so I like this one because then we don't have to use the product rule at the top. So we still multiplied by 1, but it was 1 in the form of x to the -1 over x to the -1. Okay, part 2 of the scaffold. So we want to use one of the L'Hopitals. At the limit as x goes to infinity, the limit as x goes to infinity of log y, well, we just wrote log y in this very nice form. So this is apparently the limit as x goes to infinity of log 1 plus 1 over x over 1 over x. I can erase this chunk over here. So do you remember the name of the variant of L'Hopital that we want to use to compute this limit?
I believe it is thinking. Oh boy. Infinity over infinite now.
Well, they don't go to infinity. I think 1 over
Right.
x goes to 0 as x goes to infinity, right? What does log 1 plus 1 over x go to as x goes to infinity?
It also approaches 0.
Yeah, because log 1 is 0. Good, so this should be 0 over 0 at infinity, right?
Right.
Okay, but that's good, because that's one of the valid ones that we're allowed to use. So if we say, okay, 0 over 0 at infinity is something that we are allowed to L'Hopital, then what do I get when I take the derivatives top and bottom?
So taking loud noises, taking the derivative of the top and bottom, we are going to start by chain ruling the top to see that we're going to have 1 over 1 plus 1 over x times negative 1 times x to negative 2.
Good, I'll put it downstairs, but yeah, looks good. Okay, and the bottom?
Yeah. Loud noises, Mason's throwing stuff.
Mason sounds so angry.
What was it doing? We are also taking the derivative of the bottoms to get 1 over negative x root. Excuse me, negative 1 over. My god, if I can make up my mind. 1 over. Pain. Negative 1 over x squared. Wow. I can read.
Good, good, good. Okay. So the nice thing, we get some cancellations. So you can kind of just look at it. What is the value of this limit as x goes to infinity of 1 over 1 plus 1 over x?
1.
Good, okay.
Woo!
So that's very interesting, because now we can just take the exponential of both sides, because ultimately we're trying to find the limit of y, not of log y. So we want to get rid of this log, but we should be careful about how to do it, because it's not always true that a function of a limit is the same as the limit of the function. That's not always true. It is true if the function is continuous. So this is why we need to appeal to continuity here, but thankfully we know that the exponential function is continuous, right? So I'm going to just drop in a fat old e on either side. And just to be clear, when I write the letter e here, I'm not talking about the sketchy definition. I'm just talking about the base of the natural log. This is the old definition, right? So this is the function which undoes log, right? So anyway, so if I write this, and if you believe my claim that continuous functions commute with limits, you can switch the order of applying the function and taking the limit, then what do we conclude from the left and right sides of this equation?
I am trying to remember. Take the exponential of both sides. What does take the exponential mean? Is that multiplying by e on both sides? Oh, x on both sides. Okay.
Yeah, that's what I was doing.
So this is going to be equal to, well, y equals.
Well, there's still a limit, right? So
limit of x to infinity of y equals e.
good. Okay, but this is pretty nice, because what did we just prove? Well, the limit as y goes to infinity, the limit as x goes to infinity of y is exactly the sketchy definition I wrote down way back when we were proving this derivative. So what has this proof done? This proof has showed that, one, this sketchy limit that I wrote down actually exists, right? The limit exists, and it's well defined. Better, we've proven that the value of that limit is the same as our old familiar definition of e as the base of the natural log, right? The thing which kills log when you left apply it. So that's nice. Now we know that our two sketchy, our sketchy definition and the real definition are consistent, right? The limit exists and it's equal to the base of the natural log. So this is pretty good for internal consistency check. Okay, thoughts on this?
I do not have any thoughts or questions.
Okay. Let's do more things. I think this is almost identical to what we just said. Take log of y, simplify, write as a quotient, 0 over 0 at infinity, differentiate, these guys cancel. Using this continuity argument, which means this chunk. Limit as x goes to infinity, 1 plus 1 over x dx is e. So the definitions agree. Okay, so one thing you might reasonably complain about, you could say you could accuse me of pulling a fast one on you, because when I gave the sketchy definition, it wasn't an x, right? I said the limit as n goes to infinity, where n is an integer, so n could be, say, 1, 2, 3, and I said something, I waved my hands and said some words like if you plug in larger and larger integers, this limit will tend to some quantity, right? This was the motivation I gave when I gave the bacteria story for, I forget where this was, one of the early daily challenges. I gave the bacteria story to motivate the definition of E, and we used n as an integer, the number of cuts, how you cut up the day into different dividing periods or something. So you might say, well, you've just proved that for a limit as a continuous real variable x goes to infinity. But this is inconsistent with what you told me before, because you told me something about an integer going to infinity. So what does it even mean for a limit of an integer going to infinity? We haven't defined that. And I concede, yes, you're right, we haven't defined that. So there will be, I think, chapter 7 on sequences and series. We will go into much greater detail on this. This is kind of the proper place to make this definition. But I'd like to preview that slightly just because I want to close this gap about this strange definition that I gave. So here's one preview from chapter 7 about sequences and series that says what this means. So anyway, fine. Let the set of the an, let an for n being a non-negative integer, be a sequence of real numbers indexed by an integer n. So this is just, there's an a0, an a1, a2. For each integer, there's a number a associated with that integer. So it could be like this sequence. It could be the sequence of just, 1, 2, 3, 4, 5, dot, dot, dot. You could have the sequence of all of the 2 to the n's. So you would start with 2 to the 0 as 1, then have a 2 and a 4 and an 8 and a 16 and so forth. You can make any sequence you want, right? Just a bunch of numbers. I will define what it means to take the limit as the index n goes to infinity in a sequence. The definition is that we say the limit as n goes to infinity of a sub n equals L, some capital L, if for all epsilon greater than 0, there exists a m, some large integer m, so that whenever the index in your series is bigger than that m, then the number in your, series, I keep saying series, the number in your sequence will always be within distance epsilon of L. So again, it's just like the ordinary epsilon delta definition for functions, except now these are sequences. So the condition is that the index in your sequence is larger than whatever m you found. If the index is larger than m, the number in the sequence is within distance epsilon of L. So that defines a finite limit. You could play the same game that we've been playing for the past 2 or 3 units about defining limits at infinity. So you could say the limit as n goes to infinity of a sub n equals infinity, where again we're defining this entire collection of simples together. Infinity is not a number. But we say that that's true if for any large number n greater than 0, you can pick a large index m, so that whenever the index of your series n is larger than that large index, then the number in the sequence will be bigger than this n. So this is just like the limit at infinity definition for functions, but again, now the condition has to do with the index rather than the input variable x. Okay, just a preview, but good for self-respect to make these definitions sensible. Okay, questions on this?
I have no thoughts or questions. I find it interesting that you're almost perfectly keeping on time with, I think slide 8 was like 5:40 your clock. And you have 24, 25 slides. I don't know why I'm commenting on this. It's just a random thought.
Yeah, so the timing is working out pretty well for this one. It doesn't always happen. Last time was a bit slow. Okay. Good. One more challenge in this section, and then I'll give you the proof of the hard thing. So first, anyway, so what are we doing in this section? Well, I gave you three versions of L'Hopital: 0 over 0 at a, 0 over 0 at infinity, and infinity over infinity at infinity. We already proved the first one, 0 over 0 at a. Now I will ask you to prove 0 over 0 at infinity. But this one's actually not so hard because we proved a result last time. So this was the last thing we did last time, was this proposition that if you have some function f and the limit as x goes to infinity of f is going to be the same if it exists as the limit as this other variable z goes to 0, where now you plug into f this function 1 over z. So we proved this last time. It's not very deep. It's just this change of variables of replacing x by 1 over z. So anyway, you can use that to prove this result in this challenge, and it's actually pretty short once you do it. So anyway, so what's the statement? The thing we're trying to prove is that if limit as x goes to infinity of f of x equals infinity, which is the same as the limit as x goes to infinity of g of x, and the limit of the quotient of their derivatives exists, then we want to prove that the limit as x goes to infinity of f of x over g of x exists, and it happens to be equal to this other limit, f prime over g prime. So that's what we want to prove. What should we do to prove this?
I am present and thinking.
Okay.
From this if, it's looking like you're implying that f of x at infinity is infinity. Oh, wait. No. Perhaps I wasn't paying enough attention.
By this statement, you mean? The sign at the top?
Yes.
Yeah, that's true. So for instance, this would work if, say, f equals x squared, right? Because x squared clearly goes to infinity as x goes to infinity. So that is true. Oh, did I write the wrong thing? Did write the wrong thing. Why did I write infinity? You're right. I should be saying 0. Good. Okay. Thank you. I don't know why I said that. 0 over 0 at infinity. I'm getting overly excited. Okay, apologies if that was why the confusion happened. Yes, this is 0, and we're still trying to prove this, but we're assuming these are 0. Okay, so with the correct problem statement, good. What do you think we should do to prove this one?
Wait, that's a long-winded way of... I'm just looking at this proposition now. I don't know why it's taking me so long to look at these things. I guess we can start by... I did not cut off, I'm thinking.
Okay. Let's see, maybe we can start with these two statements here. So we know the limit of f as x goes to infinity is 0, and the same is true of g. So can we use our proposition to replace those two limits by statements involving a different variable, like z?
Yes, we can, but I don't see how that helps us.
Well, let's just follow our nose, because if the proposition was given as a hint in the challenge, then it might be a good way to start. So, okay.
Alrighty, so...
What should I write?
Yeah. We are told in the proposition that the limit of f of x, the limit of f of 1 over z, I'm still not getting this right, limit of f of x as x goes to infinity is equal to limit of f of 1 over z as z goes to 0, and all of these equals...
Sorry, cut out at the end. They're all equal to what?
0.
So that's true. And then we have the same junk for g, right? So g of x is the limit as z goes to 0 from above of g of 1 over z. That's 0. Okay, so we know that. Now, the thing we're trying to show exists, the limit we're trying to calculate is this one, right? We want to calculate this limit and show it's equal to this. So why don't we start by writing down the limit we want to compute. So want to compute this limit. Well, let's see. This is...
Oh.
You see where I'm going?
Oh, never mind. We are using something about at 0.
Something about... Yeah, I think we want to convert this statement into a statement at 0 and use the old L'Hopital we've already proven. That's the goal. Right. So...
Okay. Or at some a, not specifically 0.
Yeah, at a. Good. Okay, so what should I write? What should I write if we're going to follow that strategy?
So we would like to compute the limit of f of 1 over... f of 1 over z over g of 1 over z as z goes to 0.
Looks good. Z goes to 0.
And we can apply our old L'Hopital's rule to my knowledge.
Yeah, because this is 0 over 0 at a, as you said, where a is 0. Okay.
Right.
So what does vanilla L'Hopital tell us?
This is going to be equal to the derivative, and in this case, by the chain rule, we're going to have f prime of 1 over z times, trying to remember, over negative z squared.
Yeah, I'll put that there. And then the bottom.
And identically, g prime of 1 over z times 1 over z squared. Well, negative 1 over z squared.
Good. That's some magic. Right.
Lovely.
Okay.
Cancel. Oh.
Yeah, so this is the limit as z goes to 0 of above, as you said, of f prime of 1 over z over g prime of 1 over z. And now I think we're almost done, because we can convert this back into a statement about x's. What is this in terms of x's?
I believe we can say if we convert this back to x's, that this is identical to the limit of f prime of x over g prime of x as x goes to infinity.
Good, perfect. Yeah. So this step is just another application of the proposition. So now we're just applying this proposition to this the whole function, the ratio, right? If either of these limits exists, we know that this one exists, which is the right side, then it's equal to the one on the left side, where here f is this f prime over g prime. Good, but that's exactly what we wanted to prove, right? Because the thing that we started with, this thing on the left, was a rewriting of the left side of the thing we wanted to prove. And the thing that we ended with, over on the right side, is exactly the right side of what we wanted to prove. So we've shown that these two limits are equal for the case of 0 over 0 at infinity, which was the goal. Good. Thoughts on this proof?
That was a lot less painful than I expected for the word prove.
Not all proofs are messy, right? Sometimes they're just very simple tricks. Okay. Yeah, I think this is basically what we just did. Yeah, swap this for a limit of these quotients. Top and bottom go to 0, as you say. Apply L'Hopital for 0 over 0 at a, which we proved. Get these minus 1 over z squareds, which cancel. Get this ratio, and then convert back to a statement about x's. So not a bad proof. The next one is much worse. So before, well, if you can brace yourself for the difficult proof, but before we do that, any comments on the previous sections?
Could we... Oh, okay, I see why this might be more difficult.
Yeah, we can't use the same trick anymore, right? Because we, in the last trick, we bootstrapped. We used one of our existing proofs, because we already proved L'Hopital for 0 over 0. We can't use that trick here, because there's nothing we can reduce it to. You can't reduce it to a solved problem. So we have to basically redo the original L'Hopital proof, which had, as you recall, a lot of fucking around with epsilons and deltas, and was kind of a pain. So we have to go through that whole thing again. Sorry.
You have to go through the whole thing again.
Well, you have to listen to my fucking spiel about it, so, I mean, you are the one in the unenviable position here. Okay, other thoughts?
Why isn't everyone just in pain?
Existence is pain. Okay, well, we should dive in, I guess. So, since this proof is harder, I'm going to start with two easy lemmas. So these will be things that help us in the course of the proof. So this is actually something I used before when we were being sloppy. Remember that first thing about square root of x being dominated by polynomials? I actually used this in that proof, but didn't prove it. So now I'm kind of covering my ass and proving it, but also because we're going to use it in the second lemma. So here's the statement. It's pretty obvious. If f goes to infinity, then 1 over f goes to 0. Right? Pretty obvious. If something is growing without bound, getting arbitrarily large, you should think the inverse of that object is going to 0. And actually the reverse is true. If f goes to 0, then 1 over f goes to infinity. Right? Pretty obvious, but we should prove it. So the proof is 2 lines. This one has a finite limit, 0, so we have to do the epsilon business. So hand me an epsilon. I have to tell you how to pick an n. Well, we know that this limit already exists, and the definition of this one tells us that for any big number, I can find an n so that f will always be bigger than the big number when x is greater than n. That's the definition of this, which we assume is true. So if that's true, I say use that definition to pick such an n, so that whenever x is bigger than n, f of x is bigger than the number 1 over epsilon, which is well defined because epsilon is not 0. Okay, well if you hand me that n, then I use that same n for the n in this thing that I'm trying to prove. Why does that work? Why does the same n work? Well, pretty clearly, whenever x is bigger than n, just taking the inverse, raising both sides of this equation to the minus 1 power, which flips the direction of the inequality, 1 over f is less than epsilon. So that completes the proof, because I've shown how to make 1 over f smaller than epsilon for whatever epsilon you hand me. You just do this. Okay, so that's fine. Another lemma that uses this, also kind of obvious, let f be a function that goes to infinity, and let a be some constant. Then the limit as x goes to infinity of f plus the constant over f equals 1. Again, this is kind of obvious, and I've been using it in a hand-wavy way before. I think I made this argument a while ago that kind of, if you're being sloppy, you could say, well, if I want to know what this limit does at infinity, I should say if x is huge, if x is like a trillion, then a trillion squared is so much bigger than 1 that I can effectively drop this. And then I'm left with a trillion squared over a trillion squared, which is 1. So that's kind of sloppy reasoning, but we should actually prove that something like that is true. And the proof is again very short. So we're trying to compute this, f of x plus a over f of x. This is a sum in the numerator, so of course we can simply split it into two fractions. The first fraction is f over f, which is 1. The second fraction is a over f. And we've proven in the lemma above that if f goes to 0, then 1 over f, f goes to infinity, then 1 over f goes to 0. So this limit goes to 0 because it's a constant times 1 over f. This is a constant as well, so this is 1. So we have 1 plus 0, which is 1. Okay, so this part's not hard, just verifying two things that are fairly intuitively clear. So thoughts on the lemmas?
I have no thoughts.
Sometimes people, instead of lemmas, say lemmata, because it's a Greek word. And in Greek, you pluralize by adding ata.
Is that actual latex?
Is this actual LaTeX, this thing?
Yes.
I mean, yeah, you can type the word lemmata in LaTeX if that's what you mean. You can type whatever letters you want.
I was thinking that for whatever reason they added in just a way, I don't know, some special formatting of lemmata.
I think one of the standard proof environments might have that built in, where you can do like, the one environment I know is /new theorem, so I think there might be /new lemma /new lemmata or something, but I'm not sure. Maybe. Good. Okay. All right. This is going to be fun, but try to keep the big picture. Okay. What are we trying to do? Two functions f and g. We assume they're differentiable on some open interval containing infinity on the right endpoint. And the proof we're doing is infinity over infinity at infinity, right? So we assume the limit as x goes to infinity of f is infinity, and the limit as x goes to infinity of g is also infinity, and the limit of the quotient of their derivatives exists, and it's some number L. Then what we're trying to prove is that the limit of the quotient of the functions f and g exists, and it's equal to the same number L. That's the point. So how do we prove this? It's going to be a pain, but let's do it. So we're trying to prove this limit exists, which means if you hand me an epsilon, I have to show you how to pick an n, so that whenever x is bigger than that big number n, this ratio is going to be within a given distance of L, less than epsilon distance. So hand me the epsilon, fix an epsilon greater than 0. The first thing we do is we use the assumption that this limit exists, the limit of the quotient of the derivatives. So if that limit exists, by definition, we can find a number m so that whenever x is greater than m, this thing, f prime over g prime, is within distance whatever we like of L. I'd like to emphasize that since this limit exists, this is for any, I'm going to use a different letter, epsilon prime, because we've already fixed epsilon, for any epsilon prime we want. Why am I emphasizing this? Because since we're using that this limit exists and we can pick whatever epsilon prime we want, it is convenient. You'll ask, why did I put a factor of 4 here? It'll cancel a 4 that comes up later in the calculation, and it will look prettier. So I'm choosing, since we can pick any epsilon prime we want, I pick epsilon prime to be a quarter of the epsilon you just handed me. Right, so hopefully the logic is clear. You hand me an epsilon, I say, hey, this limit exists, so I can pick whatever I want, and I'm going to pick a quarter of what you just handed me. So, okay, that's the first step. Use this to get an m so that this is true. Now we have to use this other thing. We proved this Cauchy mean value theorem a while back, which we used in the first version of L'Hopital's rule. This might look unfamiliar. I think the way I wrote it before was by multiplying through. So I wrote it as g prime of z times what we would call here f of x minus f of m equals f prime of z times g of x minus g of m. So I wrote it that way when we first proved it. Now I'm just dividing out, which, if you're going to divide out, you should argue that the denominators are non-zero, by the way. How do I know g prime is non-zero? How do I know this is non-zero? I'm actually going to skip those, because in the first L'Hopital proof, you might remember I said, okay, we have to show the denominators are non-zero. Suppose by way of contradiction that g prime of z equals 0. Then I used the mean value theorem to get a contradiction, because it would show that the derivative is undefined at some point on the interval, and it was just a bit of a pain. So since that argument is very similar to our first L'Hopital proof to show that the denominators don't go to 0, I'm just going to skip it and say, okay, I could argue that they're non-zero, but I won't, so we can do this. So anyway, the punchline of this slide is we can find a z in the interval from m, which is the m that we picked up here, up to x, where this is true. It has to be at least one z. Okay, questions on the first slide?
I have no questions on the first slide.
Okay. Is it no questions because it's all reasonably clear, or because it's so opaque that you got lost already?
It is all clear.
Oh, okay, good. Okay, so next I want to combine these two results, because I will point out quickly that as soon as my pen starts working. There we go. So we can combine these two conclusions to get something new. What's the new thing? Well, we know whenever x is bigger than m, this thing is true. We also know z is bigger than m by construction, because z sits in this interval from m to x. So z is bigger than m, which means this thing is true if we replace x by z, right? Because z satisfies this assumption, so it satisfies the conclusion. So if this thing is true, when we plug in this value of z, then I can take the left side of this equation, because the ratio with the z's inside is equal to this chunk. So on the next slide, I'm just going to rewrite this entire inequality using this expression in the box, right? So since they're equal, I'm going to plug that in for this limit involving the epsilon, or the inequality involving the epsilon over 4. So imagine plugging that in, and you get this. So whenever x is bigger than m, this thing is going to be within distance epsilon over 4 of L. Okay, now at this point in the proof you might be wondering, how is this helping us? We are trying to prove something about f over g, right? What we want, bad less than, what we're trying to prove is that f over g gets close to L. And all you're doing is manipulating, doing algebra parkour with this weird ratio of f and m and all this junk. So how do we convert this junk into a statement about f over g? Well, here's the trick. You say, well, fine, I'll define a new function j, and let's just look at the pieces. So j, if you look at the top of this guy and the bottom of the right factor in this multiplication, this is the f over g we're interested in. So j has, the f over g we're trying to get. And then the other pieces, the top right and the bottom left, these two pieces are exactly 1 over the thing inside the result that we just got. So this j is roughly the thing that we want divided by the thing that we have. Right? So in other words, this thing that we want equals the thing that we have control over, times j. So j is just this trick to change what we have into what we want. Okay. So you say, fine, all right, maybe I wouldn't have thought of that, but I'll concede that you're allowed to define that j. Sure. Then what do you do with it? Well, now we use our lemma. So we'll take the limit as x goes to infinity of j, where I've written, again, the product of the two pieces here. So take the limit as x goes to infinity of j. We actually know that both of these limits exist by our lemma, so we can split it into two separate limits and multiply them. So why does this exist? Well, this is just that thing that we just proved. This is like f of x plus a over f of x, right? This is that second lemma we had, where if you have one guy that goes to infinity and then you add a constant right down here, right? This guy goes to infinity, you add a constant upstairs, divide by the same guy, it goes to 1. So we just apply that here, because g goes to infinity by assumption. G of m is just some constant, right? M is a number, right? So this is like a. So this thing goes to 1. What about the first term, you might say? Well, this is just 1 over that, right? This is like f of x minus m over f of x inverse, right? This is 1 over the form in our lemma. But we've proven that if a limit exists and it's not 0, then the limit of 1 over that thing also exists, and it's 1 over the limit of the original thing. So if the limit of the thing in the parentheses here exists, which it does, and it's equal to 1 by our lemma, then the limit on the left exists, and it's equal to 1 over 1. Maybe I should have written this as 1 over 1, but that doesn't really matter. 1 over 1 times 1. So anyway, this is where the lemma helps us. We know j goes to 1 at infinity. What does that buy us? Well, now we think back to the definition. What does it mean for a function to tend to a value at infinity? The definition says for any big number, you can find a big value of x, so that whenever x is bigger than that big value, the function is within some distance, maybe epsilon double prime. You can pick whatever distance epsilon double prime you want, and there must be some n, so that j will be within that distance, epsilon double prime, of the limiting value, which is here 1. So since we can pick whatever epsilon double prime we want, again, this is kind of a strange choice, but this is something you discover after doing exploration and deciding what choice should go here to make it work. So this is our value of epsilon double prime, which will be convenient later. You take the min of 1 and the starting epsilon that we got handed on step 1, divided by 2 times the absolute value of L, which was the value of the limit that we want this to go to. Now I should comment that we actually should handle two cases, L equals 0 and L not equal 0. Because when L equals 0, this thing that I've written down is undefined. So when L equals 0, you can just not use the min. Just pick epsilon double prime equals 1. Right, so just throw away the second piece if L is 0. Okay, so we're almost done. Now, by the definition of a limit at infinity, we have to prove, since this is our n, this is the answer that we're trying to convince our opponent who has handed us the epsilon, and the opponent hopes that we can't find an n that guarantees that this will be within the epsilon that he picked of L whenever x is bigger than the n that we picked. So we've picked our n. The die is cast. We have made our move in this game. Now we just have to show that we've won. Right? If you pick this n, we have to prove that the ratio whose limit we actually care about, this thing, will be within distance epsilon of L. So that's what we have to do on the next slide. That's just a tedious calculation, though. So again, let's split it into two cases. In the case where L, the limiting value, is not 0, then let's just calculate. If x is bigger than the n that we picked, notice that that means j of x must be less than 2 in absolute value. Why is that? Because, well, if j of x, absolute value of j of x minus 1 is less than the min of 1 and epsilon over 2L, this could be at most 1. So certainly j of x minus 1 is less than 1. So if you just split this, one of the things that this implies is that certainly j of x is less than 2 in absolute value. Because if it were bigger, this would be false. So this is just splitting absolute value inequalities into piece inequalities. But okay, so that's true. Then let's just do some crazy algebra gymnastics. We take this thing that we want to prove is close to L. Right, so if we go back, remember, j was the thing that converts us between what we had and what we wanted. So f over g is this junk times j. So in the first step, I just plug that in. Here's f over g. I plug in that junk times j. All right, so that's fine. What the hell happened in the next step? Well, I did two things. First, I added 0 inside the absolute values. So add 0 in the following form. Lj minus Lj, right? J of x if you prefer. So I add L times j of x, then I subtract L times j of x, and then I use the triangle inequality. So any absolute value of the sum of terms is, this should be less than or equal to, it's less than or equal to the sum of the absolute values where you split the terms into the two pieces. So I took the minus Lj and put it in the first piece. I took the plus Lj and put it in the second piece. And I kept the L in the second piece. That's just triangle. Okay, so then the next part's not so complicated. Maybe, adding 0 was the only tricky part. Now it's just some algebra. So notice in this first term, both of these guys have a j. So I can factor a j, well, an absolute value of j, because it's inside an absolute value. But I factor out that absolute value of j outside this chunk, and I factor out L, since both of these guys have an L, so I factor out L in this chunk. And now we're in good shape, because absolute value of j, that's less than 2. This thing, this whole junk, is the thing that we went to great pains to show is less than epsilon over 4, with that convenient factor of 4. And this thing, we picked, this was less than the minimum of 1 and epsilon over 2 times the absolute value of L. So if he's less than that min, he's certainly less than each of the two things inside the min. So on the next line, that got kind of sloppy, but I just combined all those statements. So j is less than 2, this chunk is less than epsilon over 4, L stays the same, and this thing is less than the min, so he's less than that. But then lo and behold, the magic happens. Everything was cooked up carefully so that L's cancel. This is an epsilon over 2, and we get epsilon over 2 plus epsilon over 2, so this thing is, of course, less than or equal to epsilon. So with all that magic, putting together the different pieces and summing, we have proven, in that case, when L is non-zero, that the thing we want is within distance epsilon of L. One last niggling doubt. Some ugly dude could come along and say, well, what if the limit value L equals 0? Then your proof breaks, because you divided by 0 here. So then you go to hell. And then you say to the ugly dude, well, fine, I will handle that case separately. If L equals 0, you choose n large enough so that j is within distance 1 of 1. Remember before, instead of 1, we had min of 1 and epsilon over twice absolute value of L. So if L is 0, you say, fine, don't use the min, throw that away, just make it less than 1. And then the rest of the proof still goes through, because this thing is going to be, let's see, that'll be 1. And the second term in the next to last line I said was 0. Why is that true? J of x minus 1 is less than 1. So this is, oh, well, because, duh, of course it's 0, because L is 0. Why did I confuse myself there? Yeah, so in the case where L equals 0, this term goes away. This term goes away because we're multiplying by L. So then in that case, this term goes away, and we get 2 times epsilon over 4, which is less than epsilon over 2, which is certainly less than epsilon. So alright, the ugly dude has been defeated. The proof goes through when L equals 0 as well. So that's it. With all the pain, we've actually proven it. So to summarize what we did, we said, alright, adversary, hand me whatever epsilon greater than 0 you like. I showed explicitly how to pick an n. You pick an n. And then we proved that whenever x is bigger than that n, then the absolute value of f of x over g of x minus L is less than epsilon, which is by definition the statement that these limits are equal. Okay, hard proof. Thoughts on the proof before I make remarks?
Why is the ugly dude the ideal mathematician?
I don't know. I could make a mean comment about how mathematicians tend to be ugly, but I don't actually think that's true. I don't know. I stole that comment from Tony Z's book. I think I told you about Tony Z's group theory book. He often uses that term whenever he would like to tell you that, you know, you should consider a case where someone makes a change to your argument by making a poor choice of some parameter. He will use the phrase, suppose an ugly dude comes along, right? Like what we did with the symmetry stuff. I said, suppose an ugly dude comes along and picks an ugly matrix and conjugates by that matrix. So I just like that phrase.
Lovely. I don't know why I say lovely.
That's kind of fun. Okay, so we're basically done. I don't want to do these. If we had more time, I would put them on CD4, but I think you're probably pretty saturated just trying to get the existing CD4 problems done. So if we had more time, I would...
Also, there's already 17.
Oh, the 17 problems on it? Yeah.
I think so.
Many of them you've done, though.
True.
I think there's only like maybe, what, 5 or 6 that have to be done yet, or something?
About 1 week, yeah.
Yeah, good. So,
I say 1 week because, like, 1 daily challenge a day, I don't know.
yeah, that would be, I think, a good plan, because let's see, we want to have those done by session 40, so that's, let's see, 38 will be Thursday. 39 is next Monday. 40 is next Thursday. One of these should be a British tutorial probably, and then we can do integration.
Oh no, it's British tutorials again.
What? Don't you like those?
Hmm.